Good afternoon, everyone. Today, I'm going to present our work titled What You See is What You Get, Attention-Based, Self-Guided, Automatic Unit Test Generation. I'm Xingying from Zhejiang University. In this talk, I will walk you through 4 parts: introduction, approach, experimental results, and conclusion. Software defects can severely impact software functionality and may lead to significant losses. In recent years, various approaches have been proposed to detect software defects, which can generally be divided into 2 categories. The first category includes defect prediction methods. These methods aim to identify potential defect-prone modules or code fragments within the software. They typically rely on historical data and statistical models to analyze code features and predict which parts are more likely to contain defects. The second category involves automatic unit test generation methods. This includes traditional approaches such as Randoop and EvilSuite, as well as learning-based approaches like AthenaTest, S3Test, and Toga. However, both defect detection and unit test generation methods have certain limitations. The primary limitation of defect detection models lies in their limited confidence, which stems from 2 key issues. First, most existing models typically provide only solely binary predictions whether a code fragment or statement is defective or not. These results lack detailed explanations, such as which specific inputs or outputs might trigger the defect. This makes it difficult for developers to understand and trust the reliability of the predictions. In addition, the inconsistency of the defect detection models also undermines developers' trust. Consistency indicates that for the same input, e.g., one function, all models in the study give the same prediction, e.g., for a specific function, all methods predicted as defective or all agree that it is non-defective. Consistency can bring trust in prediction when developers make decisions. To investigate this issue, we conducted an empirical study to assess the consistency among various models. As shown in Table 1, we fine-tuned 2 learning-based and 2 pre-trained defect detection models on 3 widely used datasets and measured the agreement across their predictions. We found that the consistency between models ranged from only 51% to 58.5%. Such low consistency can significantly reduce developers' trust in these models, hindering their adoption in real-world development. The current limitation of automatic unit test generation methods lies in their low efficiency. Traditional approaches primarily focus on code coverage. These methods are often effective at achieving high coverage, sometimes even exceeding that of manually written test cases. However, studies have shown that high code coverage does not always lead to effective fault triggering. Meanwhile, learning-based test generation methods have made significant progress. These approaches are trained on specific test generation datasets and are capable of producing test cases aligned with particular testing goals. However, they often rely on randomly generating a large number of test cases to reach these goals without leveraging meaningful guidance. As a result, they still suffer from low efficiency and struggle to effectively trigger faults. In practice, generating unit tests that successfully trigger faults can help strengthen developers' trust in defect detection results. Moreover, defect detection information can be used to guide the test generation process. This can reduce the model search space and improve the efficiency of test case generation. To address these limitations, we propose Augur, which consists of 3 main stages: defect detection, unit test generation, and unit test validation. In the defect detection stage, we input a Java class file and use the Java parser tool to extract all methods. We then analyze these methods to identify potential defects. In the unit test generation stage, we further analyze the detected defective methods to locate specific faulty statements. We guide a large language model to focus on these statements in order to generate more efficient unit tests. In the unit test validation stage, we describe how Augur injects the generated test cases into the existing test suite. We also explain how Augur adds the necessary dependencies to ensure that the injected tests can be executed successfully. Next, I will walk you through the details of each stage in Augur. To enhance the robustness and performance of the defect detection model, we adopted adversarial learning and contrastive learning frameworks combined with the pre-trained model Unix coder. The three important components of Augur are as follows. For the code encoder, we use Unix coder as the code encoder in Augur to embed code features at the method level. Unix coder converts the input method into a 768-dimensional embedded representation. For adversarial learning, our goal is to enhance the robustness of the model against adversarial attacks. We use FGM to carry out adversarial attacks on Unix coder to generate the encoded samples after the attack. Contrastive learning is used to enhance the model's resistance to disturbances by aligning normal samples with adversarial samples. The training objective is to fine-tune the network so that the encoded representations of normal samples and adversarial samples are as close as possible. In the second stage, we utilize LMs to efficiently generate unit tests that can trigger errors. To achieve this goal, we need to solve the following four tasks. Task 1 is defect allocation. Given the source code of a defect method, Augur first splits the method into separate statements. Then, Augur locates the statement where the defect is. Task 2 is the construction of the prompt, mainly including the task description, class context, and specific defect methods. Because the search space of LMs is very large, these models will randomly generate a large number of unit tests for the focal method. In order to obtain high-quality output efficiently within a reasonable time, we have improved the attention mechanism of LLM. This improvement aims to guide the model to focus on the statements where the defects are located. The specific process consists of two parts: attention analysis and attention reasoning. LLM usually has multiple attention layers and multiple attention heads. For example, DeepSeek Coder 6.7b has 32 attention layers, and each layer has 32 attention heads. The attention head is a component of the multi-head attention mechanism in the transformer model. Each attention head operates independently, enabling the model to focus on different parts of the input sequence simultaneously. Therefore, we implemented the attention analysis module to select the effective attention heads that need to be modified. Specifically, we conducted subsampling from the defects4j dataset. After that, we need to define how to modify the attention of the LLM to make it focus on the specified statements. We increase the attention to defective statements by reducing the attention score of non-defective statements in the input method. Formula 3 modifies the model's attention by reducing the attention score of tokens in non-defective statements. As shown in Figure 3, Augur identified that line 6 was a defective statement. Therefore, Augur first marks the defect lines in the prompt, and then recalculates the attention weights to guide the LLM's attention to focus on the token related to the statement. After this, we evaluate the performance of modifying each individual attention head on the extracted subset. We sort all the attention heads based on their unit test generation performance on the subset. Unlike fine-tuning, attention analysis does not modify any model weights, so the computing resources it requires are similar to those of inference. The sorted attention headers are used as the configuration file at the model level. Once determined, we can perform attention reasoning on any data machine, thereby enhancing the model's understanding ability and improving its performance. During the inference process, Augur uses Formula 3 to modify the top K attention heads. The input of the process includes prompt, defect statement, and weighting coefficient, miles, and the output is a set of candidate unit tests. Our method is automated and requires no human intervention. Therefore, in order to verify whether the unit test generated by LLM can accurately trigger the identified errors, we need to automatically inject the unit tests into the corresponding test classes. Furthermore, we must also add the dependencies required for performing the test. Augur first uses token similarity to find the test class that is most similar to the generated unit test and injects it. If a unit test belongs to a certain test class, then this unit test is likely to use similar methods and classes, and share similar tokens with other tests from this test class. Then, Augur parses the generated unit tests and identifies variable types, referenced class names, constructors, and exceptions. and locate the public classes that match the identified type names to handle the unimported dependencies. If such a file happens to exist, Augur will derive the class path of this class and add import statements accordingly. After injecting the unit test into the test class and adding the required dependencies, the Augur executes the test to check whether it triggers the identified defects. Our experiment focuses on the generation of unit tests at the method level. In the defect detection experiment, we used 3 datasets, namely bears, bugs, jar, and defects forge. In the unit test generation experiment, we used defects4j and the dataset we collected from the GitHub project ourselves. This dataset was used to assess data leakage issues. We collected data after the time point of the large model training data. It is March 2023 for DeepSeek Coder. For defect detection, we use 2 learning-based defect detection methods and 2 pre-trained models as baselines. For unit test generation, we use 2 traditional unit test generation methods and 3 learning-based generation methods as baselines. In terms of evaluation metrics, we select accuracy, precision, recall, phone score, FPR, and PR/AUC as the evaluation metrics for defect detection, while unit test generation uses precision and the number of triggered defects. To evaluate Augur, we designed 3 RQs. RQN is to evaluate the performance of Augur in defect detection. First, we compared Augur with baseline on the bears and bugs jar datasets. Judging from the results, the performance of Augur on phone score, precision, and proc was significantly better than that of baselines, with an improvement range of 0.4% 20.6%. Next, we compare Augur with baseline on the defects4j dataset. We conduct training and validation on the bears and bugs jar datasets, and then test on the defects4j dataset. We found that the performance of all SOTAs on the defects4j dataset was very poor, while Augur outperformed all SOTAs in almost all metrics. Among them, the phone score of Augur was 0.276, the precision was 0.198, and the PRAUC was 0.208, which increased by 11.3% to 69.1% compared with the baseline. The results show that Augur has better learning ability than the 4 baselines. RQ2 is to evaluate the performance of Augur in defect triggering. Augur achieved better performance in the defects detected in RQ1 and all method-level defects in defects4j. Among them, Augur, based on CodeLlama and DeepSeek Coder, triggered 78 and 84 defects respectively. We also drew a Venn diagram to show the performance differences of different models. We obtained 2 observations. First, each method has the ability to trigger specific defects that other methods cannot trigger, and their performances are complementary. Overall, Augur has more powerful ability than baseline because it can trigger 50 defects that other baselines can hardly trigger. The third RQ is to evaluate the impact of different settings on the performance of Augur. First, we evaluate the role of the defect detection component in Augur. Among them, the 2 components of adversarial learning and contrastive learning make significant contributions to Augur. Combining them can achieve the best performance. Then the roles of different components in the defect triggering part of Augur were evaluated. We compared the impact on model performance of not using the attention guidance module and using ground truth location to guide the model. We found that the Augur using ground truth location performed the best because it utilized completely correct defect location information to guide the large model and avoided misguidance caused by defect location errors. Finally, we evaluated the impact of the number of candidate test cases. We observed that as the number of candidates increased, the performance of Augur would gradually improve, but after more than 100 times, the performance would gradually reach saturation. Finally, I would like to make a summary. We proposed Augur, which is a method-level approach for defect detection and defect triggering. Augur first detects the tendency of defects, and then guides the LLM to generate unit tests, triggering such errors with the help of the key information in the defect code. Therefore, Augur will provide developers with defect detection results, convincing defect-triggered unit tests, and corresponding test results. This automated approach instills confidence in developers about the results of defect detection. That's the end of my presentation for today. Thank you all.